Okay, we are doing chapter number 3, system of linear equation, and I discuss the basic of that system, what we consider our system. I just give you the quick review about the system. First, our system should be what, please? It should be
Have one solution.
linear.
The number of equation is the same as
First, he linear. Then second, simultaneous. 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 Linear mean every equation in the system must be linear. And simultaneous mean number of equation must be equal to the number of unknown variable. And the third thing is what?
non-homogeneous.
Non-homogeneous mean the right hand side of the system mean the B should not be equal to 0. And the last one we have is a non-singular system. And non-singular system mean determinant must be not equal to 0. If we have this case, it is 100% guarantee we have a unique solution of the linear system we have here now. But as I told you, the main job we have to do what? To check our system is a non-singular, but the basic definition of non-singular is what? The determinant is not equal to 0. And I told you to find determinant is not a very easy job in the matrix theory. So what we have to do, we do the shortcut. How can we approach to the determinant idea, but in a simple way here? And then you can have whatever the size of the matrix you can use to find out the determinant of the matrix here. Now, for this, we need the special matrix. The first thing we have to approach to the non-singular system or non-singular matrix. When we call non-singular system, I mean the coefficient matrix A is a non-singular. The first condition to approach it should be the square matrix. And square matrix is what? That is your matrix we have here now. And that matrix we have is what? All the rows and column must be equal here. Then we can have a square matrix. It's mean to approach to the non-singular, we should have the square matrix. And we always have a square matrix. Why? Because we are considering the simultaneous system. And simultaneous system mean number of equation is equal to number of variable. Number of equation mean rows, and number of unknown variable is a column. The same means we have a please. Then we have another special, which is a null matrix or zero matrix, which is not important. We have a null or zero matrix. All possible element of the matrix are 0 here. Yeah, this is the things we need also here. This is the things we have, that what you call it, the unit matrix or identity matrix. This is the important matrix we have here now. What is unit matrix? We say, you remember if you can have the matrix we have, and when you have a square matrix, like this is square matrix. How many part of this matrix we have? Can you tell anyone how many parts we can have a square matrix? We have a 3 part. One is a diagonal one, where I and j same. One is upper one, and in upper one, your I always smaller than j, and one below part, and in the below part, I always greater than the j. You know this one. If you have a matrix like this one, you have A11, A12, A13, A21, A22, 2, 3, and you have a 3, 1, a 3, 2, and a 3, 3. Now you can see the diagonal is the same. A1, 1, A2, 2, and A3, 3. I and J is same. But in the case of the upper part, this is your first, because first subscript always represent the row, which we call I, and second one column, which we call J. So I is smaller than J. I is smaller than J, like this. But here, your I is bigger than this one. So this is the things we have here now. So in unit matrix, we say that unit matrix is that all the element of the unit matrix must be equal to 0 if I is not equal to J, and all the element equal to only 1 if they are equal. So it's mean, where are equal? Equal are here, A1, 1, A2, 2. So it should be 1 only, and up and down should be 0. Then we call that is a special matrix we call unit matrix or identity matrix. Like this one, I give the example here, but like this one. This is a unit matrix 4 by 4. All the diagonal is 1, and up and down should be equal to the 0 we have here now. But remember that one unit matrix should be the square matrix. If you don't have the square matrix, you cannot define the unit matrix. So it's mean whatever the special matrix we define today, all satisfy this condition. They must be the square matrix. Then we have transpose. You know, transpose means you interchange row and column. This is not very much important for us here now. This is the things we have. The other case, we have the inverse matrix. Inverse matrix is what? You remember that in the matrix theory, it is generally not possible that AB equal to BA. But in some special case, AB are equal, BA, otherwise, most of the case, they are not equal. And in some case, when they are equal and their jawab, the answer AB equal to BA, the jawab is unit matrix, then always we call B is the inverse of A or A is the inverse of B, like this. As I told you, this is not always possible. And this is a way, if your matrix is invertible, that means it is non-singular. But this is difficult. Of course, I told you to find inverse is not easy job. Well, let's say I take 2 by 2 here. This is your A, and you find inverse by this way. And then you find when you multiply, you will see, inshallah, when you multiply AB, and then you will get the jawab is unit matrix. But we are not interested. This is some properties I gave, which is not very much important. Now, this is another special matrix we have. It's called the diagonal matrix. The diagonal matrix is a special case of unit matrix. And what is the unit matrix? You remember I give you, I say Aij equal to 0 if I not equal to 0 and Aij equal to 1 if I equal to j. So if you put the condition 1, then we call the unit matrix. If you put open it mean any number you have in the diagonal, then we call is a diagonal matrix here. So this is a special case we have here now. Of course, if you can go back to the inverse, you can see this is also called the diagonal matrix, because diagonal matrix say up and down should be 0, but this should not be 0 here. So this is a special case of the diagonal. Now, can anyone give me idea if one of the element in the diagonal is 0, what you call this one then? Anyone? For example, this is 0.
Zero matrix.
Allahu Akbar. Here we have 1, 1, 1. Only this 0. If we have any element in the diagonal, not all. If all the diagonal elements are 0, of course, we call is what? Zero matrix. If any element in the diagonal is, like in this case, if 1 in place of 1, we have 0, or in place of 1, we have 2, then we never call unit matrix. We call is a diagonal matrix. In the diagonal matrix, I never say, sorry, in the diagonal matrix, I never say that all elements in the diagonal should be non-zero. No, at least one of them should be not non-zero. We call it the diagonal matrix. Now, this is the things we need now for our case, which will easy for us to find out the idea of the singular and non-singular idea. And it is called the upper triangle matrix, special case of the diagonal matrix also. We can have here now upper triangle matrix mean, because diagonal say upper part and lower part both 0, but triangle say either up or down 0, not together, because if both are 0, we call the diagonal matrix. But if the upper part is not 0 and below part completely 0, then we call is the upper triangle matrix. If, for example, 3 becomes 0, no problem, still we call upper. We mean at least one of the upper should not be 0, then we call is the upper triangle. But below, all should be equal to the 0 we have. You understand my point, please? Like this is special case now
Yes,
here.
okay.
This is special case of the upper. This is A12, A13, A23. Not all of this one 0. At least one should not be 0. Still we call upper. But here the diagonal is 0. And this type of matrix we call special case of upper, which we call strictly upper triangle matrix. One of the method, inshallah, we will use, they need this one. Strictly upper triangle matrix mean all the element in the diagonal and below must be equal to the 0. And also another special case of the upper is if here in place of 0, 0, we have 1, 1. And below 0, then we call it unit upper. We call it the unit upper. The unit upper. Unit upper is what? The upper triangle matrix is called the upper unit triangle matrix if all the diagonal element must equal to 1. For example, this is 1, this is 1, and this is 1. Yeah, this is upper, but special case of upper, and that special case we call is what? The unit upper we have. Now, if we go reverse way mean the upper part is 0, but below part is not 0, then we call it the lower one we have here now is a lower triangle matrix. And the lower triangle matrix is what? All the diagonal element and below not 0, but upper part completely 0 we have here now. And if we have 1, 1 in the lower, we call unit lower. And if we have all the diagonal also 0 here, like this one, we call strictly lower triangle matrix we have here now. Now we have many special matrix. Let's say stop here. In the matrix theory, one of the best simple matrix we have are the diagonal one, the lower one, and the upper one, right? Why we call this one why can any student say why we call is a lower, upper, and the diagonal are the simplest matrix? Any student? because most of the element are 0. You understand me? Now, why we call 0 in that sense here? Yes. Now, if we can see here, why I call this one here? I always call D as the diagonal matrix, U as a upper, and L is a lower. You have a matrix D, the diagonal one, generalized case. What is this, the shape of this one? D11, 0, and 0. I'm right. What is next? 0, D22, and 0. And what is the third? 0, 0, and this is D33, right? This is the shape of the diagonal matrix. And this all what we wish all the diagonal elements should not be equal to 0, right? If any becomes 0, so we cannot do here, because still we call the diagonal here. Now, main things we need here, what is the determinant of the D? This is the formula, you have to remember that one, please. Determinant of D always D11 multiply D22 multiply by D33. Now, if your all diagonal element is not equal to 0, what is your D called, please?
Diagonal.
No, it's a diagonal. If all this definition will give you idea what? If all the D,
Determinant.
yeah, what is, if all not equal to 0, what does this mean? You remember when
I mean, we have the determinant. It's not equal to 0, the determinant.
it's not 0.
So it's not a singular.
Huh? It is?
So it's not singular.
Yeah, it is non-singular, right? So if someone give you the idea, it is 2, 1, and 1. You simply look the matrix D and you say this is non-singular. No need to check here. Because we know the multiplication, if all the diagonal element should be non-zero, then D always non-singular. Agree? Let's talk about U. What is the shape of U, please? The shape of U, upper one, U11, I'm right? U12, U13. What is this one? 0. And U22. And what is this one? U33.
U33.
What is that one? 0,
0.
0,
0.
and U33. This is the shape of the upper one. And we say that at least one of the diagonal is not 0. We still call upper. But what our wish is that all the diagonal elements should not be equal to 0. Why? Because we have the formula of the determinant of U always equal to what? U11, U22, and U33. You understand me? If this is all the diagonal element are not 0, what is the determinant of this one?
1 multiplied by 4 multiplied
24.
by 6.
Is 24. And 24 is not equal to 0. Oh, no need to find this one. You already see that all the diagonal element is not equal to 0. Without doing anything, you directly say this is the singular. And the same thing happen, please. Same thing happen with same thing happen with the lower one. What is the lower one? Determinant directly I give you now. What is the determinant of lower one, please? You know this one is equal to what? Always L11 multiply by L33. So this means if all the element in the diagonal part of L is not equal to 0, then we say L is a non-singular. So you can see directly without doing anything. Just look. What is this matrix? You directly say this is a non-singular, the matrix we have here. Non-singular, the matrix we have here. Now, of course, as I told you, we are not given in the exam, we are not given D, we are not given L, we are not given U. What is we are given, please? What is your linear system, please?
You have a function.
No, AX is equal to B. What is your given?
Given A.
Given A, as I told you, this is the main things we have to check. If your A is non-singular, it means your system is a non-singular. A non-singular always means a unique solution of the linear system. So what we do here, inshallah, in chapter number 3, or there are many numerical methods in the system of linear equation. What they do, they convert your A into what? The U, right? Many numerical exist. They convert A into L, and many numerical method we have. They convert A into the diagonal one. Now, when we use method to convert A into U or L or D, then we have the condition that what happened U, same thing happened to A. What happened to L, same happened to A. What happened to D, same happened to A. So it's mean we find the equivalent matrix of A, which we call U, L, and D. So when you convert A into U, then you can simply say, what is in the diagonal element of U? If all are known, 0, it means your original A is what? Known?
Non-singular.
That's the things we have to do here now, please. So what we do here, we will not use a method which convert A into D. We use the two method which convert A into U and A into L. We also have, I don't know you remember or not, you did in 107. Some method we convert A into the unit matrix. You know the Gauss-Jordan method? I don't know you remember or not. It is in the one.
Yes, yes.
Gauss-Jordan method do what? The procedure of the Gauss-Jordan method is he convert your A into unit matrix. And what is the unit matrix mean? All the diagonal elements should not be 0.
Zero.
And when it is not 0, it's mean always the determinant is the multiplication of the diagonal element. But we will not use that method here. We use only the first two cases here. But the best method in solving the linear system is to convert A into U here. Now, please, you understand now how we can approach to the non-singular idea. Don't forget, please. We will not use directly definition of the determinant because in exam, teacher never say, for check it is non-singular or singular. He will mention you, check it is singular or non-singular by using the given procedure, given method. And that's the only method you have to use, which is given by the teacher. Do you remember? You also discuss a method which convert A into U. Do you remember in 107?
Gauss-Jordan.
The Gauss-Jordan convert A into I.
In Gauss?
Yes, it's a Gauss elimination method. In the Gauss elimination method, they convert A into U. But well, I don't like the way they teach in 107. I'm not agree with them here. Because you remember what they do in 107, and when you use the Gauss method, they convert A into U and make the diagonal element of U should be 1. Wallah, this is not the procedure of the Gauss. If you do this one in 254, wallah, I will not give you the marks for that case. Okay, so be sure. If you don't remember 107, alhamdulillah, alhamdulillah. But if you remember, please forget. Okay, just say we are starting from today. Now, I give this a special matrix, which is not we are interested here too much here now. This is, I give some definition of the determinant from the basic idea for the revision if you want. Cofactor or like this is not, we are interested in that one, but for the revision, I can give you here. Cofactor or like this one, adjoint, properties. That's very much important from 254 point of view we have here. This is good for the 107 point of view, but I just give you the idea also here now. Now, the things we have here now, we say your system X is equal to B, right? We say if your system is non-singular, you always have a unique solution, right? What do you mean by non-singular? Non-singular mean inverse must exist. So when inverse exists, you multiply inverse on both sides. All right? Multiply by A, X equal to what? Into B. What is this one equal to, please? Inverse A.
X equal A inverse B.
So we A inverse A always equal to unit matrix I1. So we simply say X is equal to A inverse into the B. And we know in our case, B never equal to 0, inverse exists, you simply multiply that one and you have the unique solution. And this type of method we call inverse matrix inversion method, but we are not using this one idea there. But you shouldn't remember that one idea there. So now what information we need for our case? We finish now, please. Right. Now I repeat again. If your system is linear, your system is simultaneous, your system is a non-homogeneous, your system is a non-singular, always you have a unique solution. The only difficult part to check this one is how to check a system is a non-singular. That means the A is a non-singular. For this one, we have to work that one. So that's, I told you, what we basically do, we will not use directly idea of the determinant, but what we will do, we convert our A into the simplest matrix, which we call is a upper one, and upper one and A are equivalent. Something happened to upper, same thing happened to A. It means we only look in the diagonal part of the upper. If it is not equal to 0, it means your original A is non-singular. And when your A is a non-singular, it's always means your system is a non-singular, and your system is a non-singular mean you're ready to get the unique solution of the linear system we have here now. Now we are approaching to we have all the basic idea, and now we find the numerical method. And you remember I told you we have two type of the numerical method, direct and indirect, direct and indirect method. And you remember in chapter number what you call 2, we use only indirect method, but in this case we use both indirect and the direct method. So first we start with the direct method, and I told you direct method is one of the simplest case of the numerical method. Here we discuss, inshallah, 2 numerical method for the direct case and 2 numerical method for the iterative case, which I mentioned here, that we will discuss, inshallah. This is, as I told you, if you're a homogeneous system, homogeneous n equation, and mean this homogeneous simultaneous system, sorry, never have a unique solution because its determinant is 0 here. This is a condition we need here, please, which I mentioned in the part. This is an important step for chapter number 3. And what is this one? He said a non-homogeneous system of n equation in n unknown has a unique solution if and only if the determinant of a coefficient matrix is not vanish. Vanishes mean not equal to 0. And when your determinant is not 0, what we call it is a the singular. Right, let's come to the first case. We have a direct method, and in the direct method, I told you we will use 2 methods. First one is called gas elimination and its variant. We will use 2 type of the gas elimination in that case. And then we use LU decomposition method. This is 2 method we use, and in LU decomposition also we use 2 cases, Dolittle and Crotts methods here. So that's the things, and I told you, when I ever use L mean lower, when I use U, it mean the upper one here. First, let's start the first method to find the unique solution, if possible. Unique solution of the linear system with the help of first direct method, which we call gas elimination method. And I told you the good point of the direct method is what? We don't need initial approximation. Second, we know how many steps we have to do to find out the the solution of the linear system. And the third good point for that is that we can have the exact solution of the problem. That means in this case, we can get the exact solution of the problem also. Now, Gauss elimination has a two-step. We are given what? We are always given augmented matrix. And I told you what is augmented matrix. A and the B. B is your right hand side. You use that one. And this is the first step. And that's the first step we call. That first step we call forward elimination step. Forward elimination step. What is this step will do? He convert your A is a given system. Let's recall this is a system, maybe given system into the upper triangle system. Upper triangle system in U and let's say call it C. That means we have to convert basic step of the forward elimination step is what? We have to convert A into is a U. U is upper one. And we finish the first step. And this step will give you idea what? This step will give you idea. You are working with what? Singular or non-singular. How can you know this is singular or non-singular, please?
By the determinant.
Not determinant. We are not using determinant. When we convert A into U, then we look the diagonal element of U should not be equal to 0.
0.
Then it is
Non-singular.
non-singular. Otherwise, it is. If any of the diagonal element of U is a 0, then we call singular. So when we finish this one, the first part will tell you the idea. You are working with a singular system or a non-singular. If it is non-singular system, then you go for the second step of the method. And second step of the method is called backward substitution. Backward substitution step. What does the backward substitution step mean? You will solve what? New system. What is your new system now? Ux is equal to what? C. And then you use the backward substitution. Backward substitution mean from down to up. And then you find the solution of the linear. You understand? This is a procedure I mentioned here now. We start with the system. The first step, forward elimination, we do. And here, it means what we have to do. We have to make this, all the element below the diagonal element, we have to make it 0. Because if all the element below the diagonal element are 0, what we call it? We call it upper one. Like we did here, we use the procedure here. And we have this, and this is the shape we have here. This is your upper system. There is say after getting the upper triangle system, which is equivalent to the original system. It means this system and original system, this one exactly the same. It means if something happened to this one, same thing happened to the original system we have. So we see here now, we look only all this element not equal to 0. It's mean alhamdulillah, our system is non-singular system, and non-singular system means we have a unique solution. We use backward substitution, this formula, and we can have the solution this one. This is the matrix form I mentioned here. We start from the augmented matrix. And then we convert into the upper triangle system. This is the upper triangle system we have here now. Now, this is the thing. So main things we have to do this one here. How to make the element below element equal to 0 to convert into the upper. We have to use two different procedures to convert over the given system into the upper system. First one is called the simple gas elimination method, or gas elimination without pivoting. Now, remember that one here. What we have to check in the gas elimination method, very simple rule. We check in the original system, like this is original system. We start with the first column and we check this element should not be equal to 0. It is 1, it is 2 million, it is negative 5,000, whatever. We don't care what is the number, but only one condition should be, this should not be equal to 0. If this is not equal to 0, then we make this one equal to 0. Then we move to the second column. We check this second diagonal element should not be 0. Then we make below and continue like this one. We approach to the upper. But if we start from here and A11 is equal to 0, then we have to interchange that row with any below row. You remember in 107, you always, whatever you want, you interchange the row. No, we don't interchange the row. We only interchange the row when the diagonal element is 0. If the diagonal element is not 0, then we interchange the row. Right? And this is called the simple gas elimination method here. And this is I mentioned here. What is the simple gas elimination method or without pivoting? This basic of this is all the possible diagonal element should be non-zero. If at any state it becomes 0, then you have to interchange that row with any below row. Any below row. That is the things. And this is a formula to find the determinant of A with the help of simple gas elimination method. Please, this is a very important formula. Determinant of A always equal to minus 1 power k determinant of U. You already know U, and you can easily find the determinant of U. I told you how to find determinant of U. And what is K? K is number of time you interchange the row. If you don't interchange the row, what is the value of K, please? K is a 0. And if you never interchange the row in the simple gas elimination, because we are not always interchanging the row, we only interchanging the row when the diagonal becomes 0. When we not interchange the row, then what is the determinant of A always? Determinant of A always equal to what? Determinant of, because you not interchange the row, it means K is equal to 0. Minus 1 power 0 is 1, so we have this one. But if you interchange one time, K equal to 1, then you have determinant of A equal to determinant of U. If you interchange the 2 times, then you have determinant A equal to minus 1 power 2, like this one here. You understand my procedure, please? You understand any question, please? Any question, please?
Clear, Doctor.
Clear, very good. So that's the way we are now. If someone asks you, what do you mean by gas elimination? So your answer should be very short. Gas elimination, we convert our given system into equivalent upper triangle system. And then we use backward substitution to find out the unique solution of the linear system if your system is a non-singular. Now we do, inshallah, next time how to solve the example with the help of this. Right. Yes, I take the attendance.